E does not equal to mc squared.
Hi everybody, I hope you've been having a great week. Today we're back to science, and in fact we're going to discuss the most famous equation in all of physics, E equals mc squared. It actually follows by applying principles of conservation of energy and momentum using special relativistic formula. And there are a few videos on the internet that explain how it's derived, and in fact Einstein's original paper on the subject I've linked below. That's not what I want to do here because that's more of a mathematical thing. What I actually want to do in this video is explain what does E equals mc squared really mean. And second, I actually want to explain why E equals mc squared is not actually the correct equation. The thing that we all quote is actually a special case of a more general formula that Einstein derived. So what does E equals mc squared really mean? Well, a lot of people say that it means that energy and mass are interconvertible, as if it's some kind of alchemy. But to say that really obscures the genuine meaning of the equation and actually covers over its most profound meaning. The actual meaning of E equals mc squared, or the interpretation, is that energy and mass are expressions of the same thing. Now wait a minute, you might say that doesn't sound particularly revolutionary. So why don't I explain a little bit what the implications of this result are, and you'll see why this is a truly mind-blowing conclusion and why it rocked physics to its absolute core. So we're all familiar with Newton's second law of motion, F equals ma basically. It defines mass in the Newtonian universe as the amount of force that's required to produce an acceleration, i.e. to accelerate an object in terms of increasing its speed or changing its direction. So Max here requires a certain force to lift up, to accelerate, and he's a pretty heavy dog, so it felt pretty heavy. Quite a lot of force was required, and the more rou he has, the more mao he has, the more dog food I feed him, the more force it's going to require to lift him up, to accelerate him. And that's what we understand by mass in the ordinary Newtonian world, right? It's the amount of matter in an object. But in Einstein's theory of relativity, and this is why E equals mc squared is so important, it's not just the amount of stuff that matters. The amount of stuff, the amount of matter in a system is not the only thing that determines how much force is required to change its direction or accelerate it. In other words, how heavy it is. Let's illustrate this with a simple example. Let's look at a system with something like 3 balls, and we can label them MA, MP, and MC. So for this kind of system, in kind of, I guess, common sense or classical physics, you'd say that the mass of this system, you'd simply add up the stuff in the system, the ball's masses individually. But Einstein's theory of relativity is E equals mc squared. In other words, if these balls were moving around in different directions, they would possess kinetic energy. And therefore, the inertial mass of the system in special relativity would be greater. What does that mean? It means that to accelerate this system would require more force if these balls were moving than if they were stationary. In other words, the mass, as defined, is not just a function of the amount of stuff in a system, it's also a function of the energy of that system. Let's give a very silly example. When you weigh yourself, maybe you weigh yourself after you get out of the shower in the morning, you've had a nice hot shower, there's a lot of thermal energy in your system. Strictly speaking, you would weigh more than if you were cold because there's more thermal energy there, and therefore the energy of the system is greater. Now, because E equals mc squared, we're dividing the energy by c squared. C squared is a huge number, and so you're very rarely, if ever, going to see the effects of this in an ordinary system. So if you heated your body up by a few hundred joules, say, and you divide that by c squared, that is a tiny number, and it's not really going to affect the mass that you see on the scales. But there are many physical systems where this genuinely does make a difference. One very interesting result is the fact that atoms do not weigh the same as if you added up all the individual protons, neutrons, and electrons together. Similarly speaking, a molecule like oxygen, O2, does not simply equal the mass of 2 oxygen atoms. And the reason is because there's energy in these systems. An atom, for example, consists of obviously the masses of the electrons, protons, neutrons, etc., but also kinetic and potential energy, the kinetic energy of motion, broadly speaking, and the potential energy of the electrostatic forces between the various constituents. Now the electrostatic, the potential energy, is more negative than the potential energy, so the overall energy in the system, so to speak, is negative. In other words, if you looked at E equals mc squared, that energy is negative, and therefore the mass is lower than the individual constituents. which is a pretty interesting result. Similarly speaking, the sun is often used as an example of an illustration of E equals mc squared. Electromagnetic energy radiated by the sun causes it to lose mass of around about 3 billion kilograms per second, which is a crazy number if you think about it. It's super heavy. But a lot of that is due to energy conversion, right? Nuclear fusion in the sun's core is actually converting one type of energy to another, and then that's being radiated away and causes a reduction in the inertial mass of the sun. This is the key insight to take away from E equals mc squared. Energy and mass are the same thing in physics. They're the same concept. They're not separate things. The more energy a system has, the more mass it has, and we understand mass as the amount of force required to accelerate an object. Now, the second thing I said at the beginning of this video was that E equals mc squared actually is not the right equation. And that's true, it's not. E does not equal to mc squared except in a very special circumstance. Einstein actually derived the following equation. E is equal to gamma mc squared. Gamma is known as the Lorentz factor. The Lorentz factor is equal to 1 over the square root of 1 minus v squared upon c squared. This is the real equation. V in this case is the motion of the object or system relative to u. What you can see here is that as v approaches the speed of light, gamma becomes infinity. And if you plug it into this equation, the energy will be infinity. This is why you cannot accelerate massive objects to the speed of light. It would require an infinite amount of energy to do so. So E only is equal to mc squared, where your v here is equal to 0. In other words, for a system that's stationary relative to u. But the real equation is E equals gamma mc squared. We've looked at Einstein's most famous equation derived from special relativity, which is E equals mc squared. Now we must move on and look at something that's actually conceptually more challenging than special relativity, or something that has had profound consequences for my field of interest in particular, which is cosmology and astrophysics. And that is Einstein's theory of general relativity. And in our next video, we'll be asking the question, what really is gravity?